Now in this video, let's look at the applications of the mesomeric effect part 2. I've already discussed about the acidity of phenols and carboxylic acids in my previous video. Now look at the basicity of anilines here. Anilines are nothing but the NH2 group attached to the aromatic ring or the phenyl ring here. These are anilines. And like ammonia, these anilines are also basic. So what is basicity? The basicity is nothing but the ability to donate the lone pair of electrons or a proton acceptor, or which can uh, accept a proton here. So this ammonia, because of the presence of lone pair of electrons here, it will donate this. As a result, the ammonia is a base. And like this ammonia, the aniline is also a base because of the presence of lone pair of electrons on the nitrogen here. It can donate and can accept a proton, resulting in the formation of an anilinium ion here. So this proves this basicity. So aniline is also basic like ammonia because of the presence of lone pair of electrons on the nitrogen here. Yes, but when we compare the basicity of aniline with that of ammonia, aniline is weaker base than ammonia, and this can be shown with the help of mesomeric effect. So when we see the resonance structures of aniline here, aniline is a electron releasing group like OH group, that is, it is plus M effect group. It will release the electrons into the system. So it is a plus M effect group like the OH group, and as a result of this plus M effect of the NH2 group, it will result in the formation of 5 resonance structures. So the 5 canonical forms can be seen here, as we can see here, as a result of this plasma effect of this NH2 group. And this is a resonance hybrid of aniline here. And there's a negative charge on the benzene ring and the partial positive charge on this NH2 group. And as a result, the electron density on the nitrogen will decrease because of this resonance stabilization, or because of the delocalization of the lone pair of electrons on the nitrogen. And will this will result in the ability of the nitrogen to donate the electron pair, and and this will decrease the acidity of aniline when compared to that of this ammonia. So the electron density on the nitrogen is less on the nitrogen of aniline when compared to that of ammonia. This is because of the mesomeric effect, or the delocalization of the electron pair on the nitrogen because of the mesomeric effect. As a result, this will decrease the basicity of aniline. So aniline is less basic or a weaker base than ammonia. Yes. And how this mesomeric effect will affect the basicity of amines, anilines here. Let's see it. Yeah. The presence of the plus M or plus I groups on this benzene ring or on this aniline will increase the basicity. This is because, for example, when we see the CH3 group here, this is the plus I group here, it will release the electrons into the system or onto the benzene ring by means of plus I effect. So this will in turn will increase the electron density on the nitrogen. So this can easily donate the electron pair. As a result, this will increase the basicity. So the methyl substituted aniline is more basic when compared to that of aniline, because the a CH3 group is plus I effect group. It will increase the electron density on the nitrogen. And when we compare to the chloro substituted one here, the chloro is the minus I effect group. It will increase the electron density on the nitrogen because it's an electron releasing group. It will release the electrons into the system by means of minus inductive effect. As a result, it will decrease the electron density on nitrogen and they will decrease the basicity of the system on the whole. So this is less basic than aniline here. But when we compare, when we come to the nitro substituted aniline here, to nitro aniline here, this nitro group is again it's electron withdrawing group. This is the minus M effect group. This is a minus M effect group. So this will decrease the electron density on the nitrogen because of this minus M effect here. As a result, this will decrease the basicity. But this mesomeric effect is greater than or stronger than the inductive effect. So the effect is seen more strongly in the nitro substituted when compared to that of the chloro substituted one. So this is least basic when compared to any other molecules given here. This is the order of the basicity of different types of anilines here. Yes. On the whole, so if there is a plus I or plus M group, which is increase the basicity here because they will increase the electron density on the nitrogen there, which in turn will increase its basicity. Yes. Let's see the stability of the carbocations here based on the mesomeric effect. So what are carbocations? The carbocations are nothing but the positively charged carbon species here. For example, here this is a secondary carbocation here. The positively charged carbon species, and this is a primary carbocation, and this is a benzyl carbocation. We can see here this is the yes, benzyl carbocation. So how these carbocations are stabilized? Yes, these carbocations are stabilized if the positive charge on the carbon species is shared by these adjacent groups. If the adjacent groups try to share the positive charge on the carbon species, then this will get stabilized. The more the number of the groups which can share the positive charge around this carbon species, the more stable it will be. When this positive charge is shared means when there is plus I or plus M effect groups. Plus I or plus M effect group. In this example, when you see this CH3 is a plus I group, it will donate the electrons onto the carbon species, positively charged carbon species. Thus, in turn, it is sharing the positive charge on this carbon, so its stability is increased. If there is only one group, this only plus I effect group, only one group is there, the stability is less because the sharing is less here of the positive charge. But when we compare, when we come to this uh, benzyl carbocation here, the positive charge on this carbon is shared by this phenyl group because this is a pH or a pH is a plus M effect group. Yes, this will donate the electrons onto the carbon species and thus sharing its positive charge by means of delocalization. And the mesomeric effect, we already know this, is stronger than the inductive effect. This carbocation, benzyl carbocation, is more stable than the other and the carbocations where there are inductive effect groups which are present here. Let's see the stability of these. Yes. The same thing here. The plus I and plus M groups share the positive charge by electron donation and will stabilize the carbocation. When we come to the comparing the stability of different carbocations here, the CH3 here is a primary carbocation, then the positive charge on this is shared. It's not shared by any other adjacent group, so this is the least stable in the order. And then comes a secondary carbocation where there are two groups which are sharing the positive charge here by means of plus I effect. So this comes second in the order, and then comes the tertiary group, where the positive charge is shared by three groups here, three plus I effect groups. So this comes third in the order. Then comes the allyl carbocation, and when we see this stability in between this and allyl and benzyl carbocation, let's look at its resonance structures before coming to a conclusion about its stability here. When we see the stability of the allyl carbocations here, there is a resonance stabilization which is possible here. There's a shift of this pi bond in between the adjacent carbon atoms, and two structures are possible for this allyl carbocation, and this is a resonance hybrid here of the allyl carbocation. And we come to the benzyl carbocation here, and I've already said this is a plus M effect group, this phenyl group. So the positive charge on this carbon is shared by means of delocalization or by means of plus M effect of this phenyl group, and as a result there are five resonance structures are possible, and this is a resonance hybrid of benzyl carbocation. And so the benzyl carbocation is more stable when compared to that of this allyl carbocation. So this benzyl carbocation is more stable than compared to that of this allyl carbocation. So let's look at this order now. Benzyl carbocation is more stable because of this plus some effect of this pH group here, because of the five resonance structures which are possible. Then comes allyl carbocation. So these two are more stable because of the mesomeric effect, and as mesomeric effect is stronger than the inductive effect, these two carbocations are more stable when compared to the other carbocations where inductive effect is operated here. Yes. Now, yeah, this is the order which is followed in the stability of the carbocations. And now when we, yeah, now let's look at the stability of the carbanions based on the mesomeric effect here. And the carbanions are negatively charged carbon species. Carbocations are positively charged, and these are negatively charged carbon species. So, for example, it is triphenyl carbanion. When this negatively charged carbon species is stabilized, when the groups which are attached to it will share this negative charge by means of minus I or minus M effect, then that particular carbanion is stabilized, just opposite to that of the carbocation. Their plus I and plus M groups will stabilize the carbocation. Here, minus I or minus M groups will stabilize the carbanions. Then if the negative charge which is present on this is shared by the adjacent groups by means of minus I or minus M effect groups, then the carbanions are stabilized. Let's see the examples of these carbanions now. Yeah, when we look at this nitromethane, this is readily react with a stronger base like NaNH2 in the presence of liquid ammonia, resulting in the formation of the carbanion. Because this carbanion is stabilized by means of resonance, there are two resonance structures which are possible for the carbanion of nitromethane. So it readily forms a carbanion because this is resonance stabilized. And the second example, when we see this, is dicyanometane also readily forms a carbanion here. There are three resonance structures which are possible here. It reacts with NaNH2 in the presence of liquid ammonia, resulting in the formation of the carbanion, which has stabilized by three resonance structures here. And the main example for this is the triphenyl methane. It readily reacts with NH2 presence of liquid ammonia, resulting in the formation of triphenyl carbanion. Yes, this triphenyl carbanion is stabilized by means of resonance. Yeah, we can see the resonance structures of this where This negative charge is shared by three phenyl rings here. If I've written here only the canonical forms, if one phenyl group is participating in the resonance here. Now, three are possible with one phenyl ring, and so six more canonical forms are possible. These are three structures shown here, so six more are possible if only this is participating here in this particular uh, exa- uh, uh, in this particular canonical forms have shown. Only this phenyl ring is participating if and these two phenyl rings are also participating. Six more canonical forms are here. So many resonance structures are possible here for the carbanion of triphenyl carbanion. So it readily reacts with NaNH2 in the presence of liquid ammonia, resulting in the formation of carbanion. But when we come to the trimethyl methane, or this is nothing but tertiary butane, there is no reaction with liquid ammonia and NH2 because the product formed is unstable when compared to that of triphenyl carbanion. Yes. So we have discussed about the applications of mesomeric effect. Uh, yeah.